They've changed the app again, so nothing's where it's supposed to be, so I'm going to make mistakes. I don't care. The first lab was very straightforward. It was one-dimensional. So the cars separated, and I don't want to belabor this too much because we've kind of talked a lot about it. I do want to talk to you about what I'm looking for you to do. The cars started at rest, with the belief being then that the momentum of the system was zero. You separated the cars by depressing the button, and that caused the two cars to separate. Something like that. Now, if we could have, we would be able to take the mass of car 1 and measure its velocity, and the mass of car 2 and measure its velocity. We'd have to probably make one of those velocities positive and one of those velocities negative based on the direction the cars went. And we should be able to show that that sum is equal to 0. Now, look, let's just do a little bit of math here. For us to show that there's 0 really means that we're showing that their absolute values are the same. Ask if you don't understand what I'm saying here, because you're going to be expected to explain this yourself. Oh, good. Yes, ma'am?
Can you just go a little bit further?
I can a little bit. I think that if I take this and assume this is true, if I assume that they equal 0, then the truth is m1 v1 equals negative m2 v2. I subtract 1 from both sides. Now, all that means is that whatever velocity I calculate here, I have to force a negative sign in there. When the truth of the matter is, I just want to make sure that they're the same number. Because I know if I subtract two numbers that are the same, I should get 0. We already know from observation that one car went to the right and one car went to the left. That part's not in dispute. So now what is in dispute is, do we have the same values here? So instead of dealing with the direction, I would really like to focus on how big are the two values. Thus, I will look at the absolute value of each momenta and see how close they are. Does that answer your question okay? So that's why I think we can just look at the values here and not worry about the negative signs or anything like that. We'll focus on whether the momentum of one car is equal or not to the momentum of the other. Now, this part's hard. We did not actually measure velocity. What we did instead is make two, and these are important assumptions because they may not be true. Assumption number 1 is that when we hit the button, the cars separated at a constant velocity. That's an important assumption. We assume the cars were not accelerating after they left each other. If they left at a constant velocity, then the velocity of the car is the distance it traveled divided by how long it took to get there. If there's no acceleration, that's the definition of velocity. If you don't like delta D, we can use delta X. That might be better for you. I don't know. I don't know what you had in your notes. What's that? Oh, okay. Now, here's the deal. That means this is M1 delta X1 over delta T1 and M2 delta X2 over delta T2. Good so far? All right, well, the next assumption. This one's a little harder to buy into, but it was your instructions. You were told to move the cars left or right so that when you triggered the cars, they would strike the ends of the table in the same instant in time. What that means is the distance they traveled for each car might be different, but they traveled that distance in the same instant of time, meaning delta T1 equals delta T2. That's the condition we tried to create. So that's the second assumption. Now here's the thing. If those two are equal, then they are the same number, delta T. So in my equation there, I can go through and get rid of those little subscripts because we tried to make sure that we moved the cars left or right until delta T was the same for both. And here's why we're able to look at the distance and not the velocity. By manipulating the cars back and forth so they hit the ends at the same instant in time, then the momentum can be considered proportional to the distance. The momentum is proportional. Not the same, not the same meaning, but they should be proportional, and because they're proportional, we can make the same comparison. So be clear in your notes that you're not actually comparing momentum. We are, in fact, comparing something that doesn't have a name, m times distance, but we know that this comparison is proportional to the same comparison we'd make if we were measuring the velocity. That's why it's important. So that's the data you took. For the first car, you took the mass of the car and the displacement of the car, and the second car, you did the same thing. So you have two data charts, M and D for one, M and D for the other. So that's your data. Now, the real thing is I've been putting an equal sign here. This is a lab. We don't actually know if they're equal. Our goal is to see if they're equal, but we don't know if they're equal. To show conservation of momentum, we're trying to test and see if they are in fact equal. Now, equal would suggest that there is a percent difference between each value that is 0. For them to be equal, the percent difference would be 0. Now, it's very unlikely you're going to get a percent difference of 0. There are more than enough reasons why. Probably the most likely, friction. When the cars were of different masses, they were experiencing different frictional forces. And that's going to definitely play a role in our answers here. I can think of 2 other specific reasons why these won't be equal. I think you should think of a couple as well and make sure they become part of your lab. Because I don't think you're going to get a percent difference of 0. But that's what I would like you to do. I would like you to find 2 things from your data. Thing number 1. I want you to calculate the net average percent difference across the whole lab. Once you've done that, I want you to tell me whether they are equal inside your margin of error. Again, you decide whether you have shown conservation of momentum by deciding if your percent difference is small enough to be within your margin of error. Now, your question probably is, well, what's the margin of error? You have to decide and explain your decision. Is it 5%, 10%, 2%? You need to decide what you feel is a realistic percent difference that should account for your error. You might not understand what I'm asking, and I'm willing to let you guys think on it for a couple days without giving you the answer. I will tell you that you should consider how different things that would cause error would change the response, and by how much. For example, you guys refused, in many cases, to use something to trigger the button. You used your fingers, which tended to slow down the car that had the trigger on it. How much? How much do you think that influenced the answer? I don't have the answer to give you. I want you to think on it. I am going to make one important assumption here, that you don't know how to calculate the difference. So if that's you and you don't want to ask, I am about to tell you how to do it so that you don't feel, somehow, like you're ineffective. A lot of people don't know how to do it or don't remember. So let's talk about how you calculate percent difference. First, and I hate to say this because it demeans you, but I'm afraid that some of you need to know this, that a percentage is just the part out of 100. That's the definition of a percentage. Because of that, it's any fraction is a percentage. Now, I'm saying this because some people don't understand what I'm going to do here, and it'll make them a little bit frustrated. But to calculate percent difference, you need to find how far apart two numbers are, and then divide by the average of the two numbers. So you calculate a percent difference. How far are they apart, and divide by their average. You can calculate a percent difference against a known value too. The only difference is that you would put the known value here and not the average. But since we don't know what the known value is, then you're going to take, as an example, m1 d1 minus m2 d2. Take the absolute value, because we don't care whether one's bigger or one's smaller. We just want to look at how far apart they are. And then divide by their average, which is, and I hate to write all this out because it is a little bit demeaning, but you just add them together and divide by 2. That's how you calculate the average. This, by definition, is going to be a ratio. And so that is the answer, but some of you don't realize that to express it as a percentage, you will have to move the decimal place over 2 places to account for its part out of 100. So if you must, I'll write this in here, but I find it demeaning to do so. All right? That's how you calculate percent difference. You're going to do that 7 or 8 times. Any questions about it? All right. The second thing I'd like you to do, I want you to notice if there's any situations where the percent difference is much higher than other situations. And I'll tell you specifically what I'm looking for. When one car is much heavier than another, does the percent difference increase? I'll say it again. When one car is much heavier than another, does the percent difference increase? Is there a trend? So let's say if M1 is greater than M2, does the percent diff increase? I'm bringing this up because, look, when the cars are sitting on the track, if one of the cars is loaded up with weights, then we know by definition there's a larger normal force on it, which means there's more friction. When you make one car much heavier than the other, does that increase in friction affect your outcome? You need to look. It may or may not. You'll be surprised. It's supposed to be rolling friction, which is very low, like 0.002. So look and see if when there's a large difference in mass, if you see a trend in an increase in the percent difference. I'm just looking for a written response. All right? This sheet of paper represents your target. You should have marked the center. That's the point directly below where the ball has left the table. At the same time, you should have a group here that represents where the ball struck the ground if there was no collision. And then hopefully you have 2 places that represent the point where the ball struck the ground when there was a collision. Now, I have noticed on some papers where your group looks like this. It's huge. That's bad. Just so you know, it should do it the same way every time. Having a large group like this means you are not careful in dropping the ball, not careful in placing the ball in the same place all the time. You might have been moving the ramp a little bit or moving the paper a little bit. A large group like this is usually bad news. Now, I can't say that that's always true. I'm just saying that that's something I look for. If you were to then take and kind of circle the data points, kind of make sure we understood where the group was, and mark the center of these groups. So center, center, center. You then had to draw a couple of lines in. The lines here represent, in this case, the distance the ball's traveled horizontally. There's that one. And then we have this one, and maybe I'll do this right. Maybe I won't. There. And this one. So you guys drew all those things? When you're done with that, I asked you to measure this angle and measure this angle. That requires a protractor. And then you had to measure this length and this length, and of course, that length. Okay? That's all the data that you should have. You might have done a few other things like calculate some cosines and sines. We'll come back to that in a minute. Any questions about this? All right. Again, in this lab, we're looking at conservation of momentum. In this lab, we are trying to isolate velocity by measuring distance. In this case, we did so because the truth is the ramp was located on a table and it was always the same height above the ground every single time. Because that's true, it took the marbles the same amount of time to reach the ground regardless of how fast they were moving horizontally. We know that the time it takes to reach the ground is based on the height, and nothing but the height. Because of that, the time it took to reach the ground was the same, whether the ball moved a long distance away from the edge or a short distance. If I want to know the horizontal velocity, if you remember from projectile motion, it's always the horizontal part, it's the range, and delta t. That equals the horizontal velocity. Since delta t was the same for all of them, we can simply compare the ranges and know that we are comparing the distance, the velocities. For this lab, this is why we can just look at the distances and not have to worry about the velocities. That does assume there's very little air resistance. And it does assume that the ball is always the same height when dropped from the top of the table. As long as you do the entire lab on the same day using the same apparatus, that should be fine. But those are our assumptions. So, I'm going to shift gears a little bit on this one. Is represented by this distance. This is the ball without striking something. That is the initial velocity. That's this and this. So your... Oh, that's not a good look at it, but... Because there's something a little different about this one that you might not have noticed. And that's this. What really is happening is we have the first ball being fired at some velocity into another ball that's at rest. After the collision, the two balls separate. Now, what we really have is this picture. This is the picture we have. The initial velocity, we then have the two resulting velocities of the collision. We have that too. The picture is really a picture of the collision, with the longer arrow being the velocity of the first ball and the two smaller arrows being the velocities as a result of the collision. The reason that's important is momentum is a conserved quantity. The ball had no momentum. I don't want to know if I want to say the word horizontal here. If I use this picture to describe the momentum of the balls, before the collision, there was no momentum in that direction. There was none. which means that after the collision, the momentum that is not aligned with the, I think on the right up on the board, I put the y direction. There. Is that more like what I had on the board? There, just like that. There was no x momentum, which means that if I look at the x momentum of each ball, they should be equal and opposite. Also, since the ball had a single y momentum before the collision, if I look at the y momentum of each ball, they should add up to equal the y momentum before. The x momentum of the ball is going to be the velocity of the ball, in this case the distance, times the sine of the angle. The y velocity of the ball is going to be the distance times the cosine of the angle. Those are the things you guys were asked to figure out. Now, the one thing I'm leaving out here is the mass. And that's because the mass of all the balls was the same the whole time. Which means this doesn't depend on the mass, just the distances. And of course, the angles. So in your description, what you should be doing, and I'll try and do this based on what I think you guys wrote down. There is the, did I use the words right and left on the board? Is that what's in your notes? What did I put in your notes? Or did I not say right and left? I said B and C, right? Let's do B and C. All right. So let's look at first the off axis, or the x direction parts. The distance to point C times the sine of the angle should be equal to the distance to point B times the sine of the angle. That's what you should be looking for, because the stuff that traveled laterally should add up to be 0. That one's pretty straightforward. The distance to A should be equal to the distance to B times the cosine of the angle plus the distance to C times the cosine of the other angle. In a two-dimensional collision, the momentum before should be equal to the momentum after. The distance to A represents the momentum of the ball by itself. The components that travel along with the ball should be equal to the total. That's why when you look at your picture, if I can draw that real quick again. When you look at your picture, which is on your square, so here's your square. You've got this long line in the middle to A. And you've got these two shorter lines to B and to C. This distance and this distance should be the same. They should add up to be the same. This distance and this distance should add up to be equal to A. Those two distances in green are those two distances. The ones that come from this, the cosine of the angle. That's what you're trying to show.